Hi everyone. Have you ever wondered how ChatGPT can read an entire sentence, understand the relationship between different words, and then generate a surprisingly intelligent response? The technology behind this is called transformers. Transformers are one of the most important breakthroughs in modern AI, and they are the foundation behind models like ChatGPT, Claude, Gemini, and many other large language models. But what exactly is a transformer? How does it understand which words are important? What is attention? And how can something as simple as predicting the next word lead to systems that can write, reason, summarize, and even generate code? In this video, we're going to break down transformers from the ground up. We look at tokens, embeddings, self-attention, multi-head attention, and the transformer architecture. And I'll also show you a simple practical example so you can actually see how attention works. So let's get started with modern AI transformers. Before transformers came along, AI models already had ways to process text. One popular approach was recurrent neural networks or RNNs. The basic idea was simple. An RNN would read a sentence one word at a time from left to right. For example, the cat sat on the mat, the model would read the then cat, then sat, and so on. As it moved through the sentence, it would keep a kind of memory of what it had seen before. This worked reasonably well for short sentences, but there was a problem. As the sentence became longer, it became harder for the model to remember information from much earlier in the sentence. And there was another major limitation. Because the model processed words one after another, it couldn't efficiently process a large amount of text in parallel. To improve this, researchers developed more advanced architectures such as LSTMs or long short term memory networks. LSTMs were much better at remembering important information over longer sequences, but they still processed the sequence step by step. So, researchers were looking for a way for the model to look at all the words in a sentence and determine which words are important to each other. And that is where the big breakthrough happened. In 2017, researchers introduced a new architecture called the transformer. Instead of processing words strictly one at a time, transformers introduced a mechanism called attention. And attention completely changed how AI could understand relationships between words. That idea became the foundation for many of the large language models we use today. So, what exactly is a transformer? At its simplest, a transformer is a neural network architecture designed to understand relationships between different parts of a sequence, especially words in a sentence. But rather than explaining that with a complicated definition, let's look at a simple example. When we read this sentence, we immediately understand that it most likely refers to the dog. But how does an AI model figure that out? It needs to understand the relationship between it and the other words in the sentence. This is where transformers are different. Instead of simply moving through the sentence one word at a time, a transformer can look at the words in relation to one another. It can ask which words are important to this word, which words should I pay attention to, and how strongly are they connected. This mechanism is called attack attention, and attention is one of the key ideas that made transformers so powerful. You can think of it almost like the AI highlighting the words that matter most when trying to understand a particular word. Of course, a computer doesn't actually understand words the way we do. Before the transformer can process this sentence, the words are converted into numbers. First, the sentence is broken into smaller pieces called tokens. Those tokens are then converted into numerical representations called embeddings. Now we have everything the transformer needs. We have our tokens, we have their numerical representations, and now the transformer can process these representations and determine how the different words relate to each other. And here's the important part. The transformer takes these numerical representations and repeatedly transforms them, allowing the model to build a richer understanding of the context. That's actually where the name comes from. The model is transforming the representation of the input as it passes through the network. So, if you remember just one thing from this section, Remember this, a transformer is a neural network architecture that uses attention to understand relationships between different parts of a sequence. And that simple idea became the foundation for today's large language model. Let us see how the OpenAI tokenizer works. This tool shows how AI breaks down text into pieces called tokens. Watch as I type a sentence: the dog chased the ball because it was excited. Notice the result. This simple sentence becomes just 10 tokens. Tokens are the building blocks that ChatGPT actually reads. Now let me click show example to explain further. Each color represents a different token. Some words are one token, but others split into smaller pieces. These are token IDs. The model learns patterns from these token sequences and their numbers. These colored sections show how embeddings work. Embeddings turn each token into mathematical values that capture meaning. The rule of thumb: one token equals about 4 characters. So 100 tokens roughly equals 75 words. This tokenization process is the first step of how transformers understand language. Back to our example, here are all the token IDs as numbers. ChatGPT sees your text as this sequence of numbers, then predicts what comes next by understanding relationships between them. The AI model learns from. That's how transformers understand language. Now let us look at the core concepts of transformers as an instance of the encoder decoder architecture. The overall architecture of the transformer is presented in this figure. Though it might look complex, don't worry, we will simplify it. As we can see, the transformer is composed of an encoder and a decoder. At a high level, the transformer encoder is a stack of multiple identical layers, where each layer has two sublayers. The first is a multi-head self-attention pooling, and the second is a position-wise feed-forward network. Transformer encoder outputs a d-dimensional vector representation for each position of the input sequence. The transformer decoder is also a stack of multiple identical layers with residual connections and layer normalizations. As well as the two sublayers described in the encoder, the decoder inserts a third sublayer known as the encoder decoder attention between these two. In the encoder decoder attention, queries are from the outputs of the decoder's self attention sublayer, and the keys and values are from the transformer encoder outputs. This masked attention preserves the autoregressive property, ensuring that the prediction only depends on those output tokens that have been generated. Next, look at the most important idea behind transformers' attention. In this sentence, the animal didn't cross the road because it was too tired. What does it refer to? When we read this sentence, our brain automatically looks at the surrounding words to figure out what it means. You can think of attention like a spotlight. When the model is processing one word, attention helps it decide which other words it should focus on. And here's where transformers become really interesting. Instead of looking at only one nearby word, the model can consider relationships between many words in the sequence. But attention isn't only about figuring out what a single word refers to, it can help the model understand many different relationships at the same time. So instead of thinking about a sentence as just a sequence of words, we can think of it as a network of relationships. This is called self attention because the words in the sequence are essentially looking at other words in the same sequence to understand their context. And this is the big idea behind transformers. The model doesn't just look at words individually, it learns which words should pay attention to which other words, allowing it to build an understanding of the context. But how does the transformer actually calculate which words are important to each other? That's where three important concepts come in: query, key, and value. The self attention mechanism is a pivotal innovation within the transformer model. To achieve this, the mechanism computes three vectors for each input element: a query, a key, and a value. The process involves a dot product between each query and key, followed by a normalization step using softmax. And finally, the resulting weights are applied to the value vectors, producing the attention vector. This vector is a representation that captures the contextual relationships within the input. The following table summarizes the steps involved in the self attention mechanism. By isolating and processing these vectors, self attention provides a nuanced understanding of the input, which is essential for the complex tasks that transformers are often tasked with. The ingenuity of the multi head attention mechanism lies in its ability to concurrently process data through multiple self attention layers, each with a unique perspective. This parallel processing enables the model to capture a richer representation of the input. By dividing the attention process into heads, the mechanism can attend to different parts of the input sequence differently, akin to how a group of experts might analyze various aspects of a complex problem. The transformer typically employs 8 such heads, though this number is not set in stone and can vary depending on the model's complexity and the task at hand. Each head captures different features from the input sequence, and their collective output is concatenated and once again linearly transformed to produce the final attention output. This multifaceted approach allows the model to be more discerning and nuanced in its understanding. Now that we understand the basic idea behind transformers, let us connect this to something you probably use every day. ChatGPT, let us type explain how a car engine works in simple words. When you send this prompt to ChatGPT, the model doesn't simply read the sentence like a human. It transforms it visually into individual tokens like this. The text is first broken into tokens, and those tokens are converted into numerical representations that the neural network can process. Those representations are then processed through the transformer, prompt, tokens, embeddings within transformer, self attention, feed forward, and so on. Inside the transformer, attention helps the model understand how the different parts of your prompt relate to each other. After processing the context, the model predicts what token should come next. It then predicts another token and another repeatedly until it has generated the complete response. So, at a very high level, this is what happens when you use ChatGPT. So, when you interact with ChatGPT, you are interacting with a language model built around the transformer architecture. ChatGPT generates text by repeatedly predicting the next token based on the context. We've talked about attention conceptually, but let's actually see it in action. I'm going to use a small Python example to visualize how attention works. Our goal is simple. Let's see what the word it is paying attention to. I'm using PyTorch and Hugging Face transformers for this demonstration. I'm using a small bird model from Hugging Face. The important part here is that we are asking the model to give us its attention values. Added the text, the cat sat on the mat because it was tired. Then let's print the tokens. First, the sentence is converted into tokens. Let us run the program. It takes a while to tokenize the string we gave as input. It prints the result. Let us zoom in to see what it printed. First, the sentence is converted into tokens. Each token is printed separately as it reads, the cat sat till it was tired. The transformer has multiple layers and multiple attention heads. So instead of looking at just one attention value, we can inspect what different attention heads are focusing on. Let us zoom to the output what we got with these additional program. We can see different layers and heads printed. This is a great place to see how the multiple attention heads are focusing on. The transformer has multiple layers and multiple attention heads. So instead of looking at just one attention value, we can inspect what different attention heads are focusing on. Let us zoom to the output what we got with these additional program. We can see different layers and heads printed. This is a great place to see how the multiple attention heads are focusing on. We started with a simple sentence, broke it into tokens, passed those tokens through a transformer, and visualized how attention helps the model process relationships between them. And that's the core idea that powers today's large language models. So let's quickly recap what we learned. Transformers changed this with one powerful idea, attention. We also saw how text is converted into tokens and numerical representations processed through transformer layers and ultimately used to generate the next token. Transformers allow AI to understand context by learning relationships between different parts of the input. I hope this video is useful. Let me know in the comments what do you think about the video. And if you enjoyed the video, don't forget to like and subscribe to AI Talks for more practical AI tutorials and explanations. Thanks for watching, and I'll see you in the next one.